computer. So let's begin again. So we were discussing multi-component universe. And the first component is the radiation. We have matter component as of today, a power of 3. And we have dark energy. And we have curvature component. And the way we write the curvature component was to write in this way, power of 2. So this is another form of Friedman equation that we discussed. And there are several advantages of this expression of the Friedman equation. Number one, it's dimensionless. Number two, it's easy to remember, although you may not agree with me. So it's dimensionless because ion tension ratio, scale factor is dimensionless, and omega, density parameter, is dimensionless. And radiation is scale factor power of 4 because of the extra degree of freedom that photon has, or radiation has in general. Matter, non-relativistic matter is just proportional to the volume, inversely proportional to the volume. So I have factor a power of 3. And dark energy component, there is no relationship with scale factor. And this curvature term has a power of 2. It's because we live in three-dimensional space and we talk about the curved space. So that's what it is. And omega 0 here was defined in such a way to be radiation 0 plus matter component 0 plus dark energy component. This is in general not equal to 1, but when this is equal to 1, this means our universe is flat universe. So that's what we discussed in previous lectures. Okay, so today we start with multi-component universe. Number one is matter plus curvature. So matter so if I rewrite this, h square divided by h0 square. I don't have radiation, I have matter. So omega. Now I only have matter component, so I don't need any other subscript. So I write simply omega 0 a power of 3 plus 1 minus omega 0 over a square for the curvature term, because we are talking about matter plus curvature term. Now to discuss something, we have to assume something. So let's assume, suppose the Hubble expansion rate as of today is positive. So somehow, right now, this universe is expanding. Then what's going to happen later on? That depends on the relative sign of these things. First of all, this term is always positive. So depending on the value of the second term, the fate of this particular universe will change. In this case, to stop expansion, this term has to be negative, so that this is h squared, meaning to stop the expansion, this term has to be 0. To have this term to be 0, this second term should cancel with the first term. So first of all, omega 0 should be greater than 1 to be this term to be negative. What that means is this is positively curved space. And the maximum expansion happens when this right-hand side becomes 0. So I have omega 0 over, let's call the scale factor at the maximum expansion to be a max, power of 3, to plus 1 minus omega 0 a max square has to be 0. So doing the calculation, a max should be equal to multiply max power of 3. So omega 0 over omega 0 minus 1 should be the value of scale factor. A long time ago, we discussed the mathematical structure of the Friedmann equation. And if your A is the solution of the Friedmann equation, then the time reversal, a minus t, should be also solution. Both solutions of Friedmann equation. So what that means is, at least formally, let's say vertical is scale factor, horizontal is time. So today is expanding, and we assume it's a positively curved. So whatever was the history of expansion, we don't know. And you reach to a max that we just computed. You don't even have to calculate how a max will shrink, because you already did. So mirror image of this curve should be the solution. Of this particular universe that we are discussing. So that's nice. But let's think more carefully. This is a formal solution, but we have in our solar system, we have sun. Sun emits light, emits photons. So according to this, universe expands and it stops expansion and it crunches back. But locally, there's a term called entropy. Increases. According to this, we have to go back to the original beginning of our universe, which means photons emitted from our sun has to be absorbed by the sun to satisfy this exact solution. But that doesn't happen. We are not getting younger. I'm sorry, but we are only getting older. So this is you have to understand that way. This solution is telling us that we are going back to exactly same state where we began, but that doesn't mean that we are getting younger back. Okay, that's one thing we have to remember. Okay, so let's erase. I was stupid enough to make this towel wet, so that we have to wait a little bit. Now we want to discuss some other cases. What happens if omega 0 is now less than 1 and kappa is plus 1? I erased the Friedmann equation, but both terms are now positive, so it will expand forever. So there is a term called, let's summarize what we discussed so far. So we can have omega 0 is less than 1, then, I'm sorry, kappa plus minus 1. Kappa is minus 1. As I said, it will expand forever. So universe become really, really chill. So people call this situation to be big chill. And the case that we discussed in the beginning, where omega 0 is greater than 1, kappa is plus 1, universe will cease to expand and it will go back to the beginning. The people call that a big crunch. I don't know who named this, but and kappa, when kappa is equal to 0, there is no curvature term. So it's still big chill, but that's the one we already discussed when we discussed the flat universe. So I'm skipping it. Now, I don't know how much detail I want to go. So we rewrite Friedman equation again. Now I use a dot square h0 and omega 0, and I multiply a square. So I have over a plus 1 minus omega 0. I used to have a square, so I only have this term. This is one of the cases where we can calculate analytically. So formally, I move h0, a dot is dA over dt. So I can have h0 t, and formally I can write the integral 0 to certain value of scale factor. And in this case, I have dA. I want to differentiate this from that. So, and in the denominator, I have omega 0 over a prime plus 1 minus omega 0. Over 2. This one we can there's an analytic solution. I am not mathematically oriented person, so I don't want to go. I don't want to give you too much hard time, but let me sketch this, how you do this integral, because this will be your homework. You can change this into 0 to a. I multiply a to the numerator and denominator. So I have a dA prime prime. And I have the square root, so I have a prime square, so I have a plus 1 minus omega 0, a square, and 1/2. The next step is you can change this into 1 over omega 0 minus 1 square root integral 0 to a dA you will change the denominator in the quadratic form. So you end up with omega 0 square divided by 4 omega 0 minus 1 square minus a minus omega 0 over 2 omega 0 minus 1 square square root. Once you did that, you can change the variable in terms of sine and cosine, and then you can finish this integral analytically. So this is a small hint for your homework. Now the thing is, when we do the integral, what that means is we are going to get the expansion history. That's what we want to know. But in this case, particular case, the analytic form is not closed form, it's a parametric form, which means instead of this, I have expression of the scale factor in terms of something else. And my t time is also expressed in terms of something else. And this parameter theta runs from 0 to some value that we will discuss later. Why do we use theta? Because as you can guess, it's related with a sine, cosine trigonometric function. And it turns out, if you do this integral nicely, 1/2 omega 0 over omega 0 minus 1 minus cosine theta. And the time is a little more complicated. It has double parameter omega 0 over omega 0 minus 1, 3 over 2, and theta minus sine theta. So let's take a look at some figure. Share screen. So let's look at this red curve only. This is what we are discussing. So basically, I'm plotting the result that I wrote on the blackboard just before. So I'm sorry, the vertical scale is the scale factor, and horizontal scale is the time normalized by Hubble constant. And as usual, the 0, we subtract t from t0 so that horizontal 0 is today. And this red dot represents so-called, big crunch. And since we already discussed, this blue thick curve is the case when omega 0 1.0, so flat universe. And as we also discussed, when omega 0 is less than 1, that means universe expands forever. And that's this green dashed line. All right, so that's what it is. But do I want to? One technical detail is when we just plotted the figure, we applied a, not just t, h0, t minus t0. So you have to get t0 here from first by how did I do that? Okay, it's a little more complicated. From here, when a today, a is equal to 1, it's called that time to be parameter theta is theta 0. So you should get theta 0 first. So from here, you get 1 is equal to 1/2 omega 0 over omega 0 minus 1. Not sure whether you can still see this. Maybe too small. And 1 minus cosine theta 0. That's theta 0. And you have to get theta 0 from there. Put that theta 0 to this equation. From there, it's in my lecture notes. I won't repeat. So you get theta 0 from this equation. I'm sorry, t0. From t theta. And then finally you subtract h0 minus this t0 to have this plot. And once you do that, you will have this nice curve. One more thing to note is here is around 110. So that let's remember this number because we will compare with other cases later on. Okay. One more thing. So a theta. So when cosine theta is when theta is 0, it's 0, but it goes from here and it goes back to 0. So when theta is 2 pi, theta is 2 pi gives you this so-called T crunch time. And T crunch can be obtained from here. 1/2h0 omega 0 over omega 0 minus 1 3/2 times sine 2 pi is 0. I have 2 pi times 2 pi. That brings me so-called crunch time. Okay. Now, let's remove half of this. Let's wait until it dries. It's good because I can take a rest. One more thing, when I take a rest is share. So the first plot is over 100 in the unit of Hubble time. But if you zoom that up, it's running from some negative value to only 3 in terms of Hubble time. So in the beginning, they behave almost similar, regardless of the value of omega 0. But the actual fate of the universe is quite different when you wait until more than 100 Hubble times. That's what we can find from this. Now, when omega 0 is negative, the integral becomes slightly different. And as we have seen something similar, in this case, A and T are also parameterized. Let's use eta, big letter eta, as the new parameter in this case. And it's quite similar, 1/2. We could compare with this. Omega 0, 1 minus omega 0. But instead of 1 minus cosine theta, we have hyperbolic cosine eta minus 1. In the case of time, 2h0 omega 0 1 minus omega 0, I suppose power of 3/2. Instead of sine, I have hyperbolic sine. Sine hyperbolic eta minus eta. So it's, I don't know why, but it's not exactly the same, but there's some correspondence. Sine, hyperbolic sine, cosine, hyperbolic cosine, but sine is flipped and so on. That's the mathematical details that I cannot answer right. All right, so that's all about matter plus curvature. Second topic is matter plus lambda. So now it's a flat universe, but we have matter and curvature. Notice that this model universe represents more or less our universe as of today, according to our observations. So we are talking about flat universe. How am I doing with the time? 41. So lambda 0 is 1 minus omega matter 0, because number 1, we are talking about flat universe. Number two, there's no radiation. So our Friedmann equation, h squared over h0 square is no radiation. I have matter component. So let's use omega matter 0. I have a power of 3. And this term, let's only use this. So 1 minus omega matter 0. This first term is always plus. Positive definite. But this guy, depending on the value of omega and 0, could be negative or positive. It's strange, isn't it? How come matter component gives you negative value? It all depends on the characteristics of dark energy, omega lambda. Because at this one, this is not independent. This is completely correlated with omega lambda 0. So let me write all the cases. If omega is simply stating basically this. If this is less than 1, this means, of course, omega lambda 0 should be greater than 0. And if this is greater than 1, this is less than 0. If this is the case, then of course, right-hand side of this is always positive because omega in 0 is less than 1. So in this case, running out of space, but this case, universe expand forever. That is the case. And if in the second case, there is a maximum value of A, so we could have omega m0 over A max. Well, let's get it, since I wrote it, should be equal to omega m0 minus 1. So if you solve it, A max should be omega m0 over omega m0 minus 1 I'm sorry for this, is equal to 1/3 because of cubic factor 3 over here. So in this case, it expands, but it stops, increase again, and it shrinks back to nothing. In this case, we could also solve this Friedmann equation. Let's see. Let's try to be this equation can be rewritten as an integral as usual. I'll skip putting the a prime. Vector out a. And here you have omega m 0 over a square minus omega m 0 minus 1. You simply switch and take negative. And next step is I'm helping your homework. You can change this omega m 0 minus 1 integral 0 to a square root a dA over a3 max minus a3 square root. Where a max is this guy. Okay. Once you did that, you could, it's constant minus variable power of cubic. So we can do this integral. One more hint. If you have that a is a max sine 2 over 3 theta and have that back into the integral, then you'll get the answer. And the answer is H0 t is equal to 2 over 3 square root omega m0 minus 1. And you have the inverse sine of something. And that is a over a max 3 over 2. Why is it complicated? I guess that's what it is. So let me summarize. We were only talking about this second case where either way, omega m 0 greater than 1 or omega lambda 0 is less than 0. In that case, there is a maximum value of A. That means universe will shrink again, just like the previous case of matter plus curvature. Yeah, matter plus curvature. And you can also say that from this solution, then you will get this is what H0 T square root omega n 0 minus 1 over 2, 3 times sine is equal to A over A max over 2. So scale factor is here. So when scale factor is 0, the universe size of the universe becomes 0. So to that happen, this value has to be, remember we have sine term, the value has to be pi. 0 is the beginning. So that means T crunch this time 2 pi over 3 H0 square root omega m 0 minus 1 if I didn't make any mistake. Seems not. All right, so that's the result so far. Now let's take a look at some plots. Share a screen. Share. This one we already discussed. Matter lambda. We did that. Where is the plot? Okay. So this is the case of matter plus lambda. And I hope you remember that here again we are expanding the time from t0 in the unit of Hubble time or inverse of Hubble constant from 0 to 100. Remember, in the case of matter plus curvature, when it crunches, it runs more than 100. I mentioned the number 110 in the unit of Hubble time in order for such universe to crunch. But in the case of matter plus curvature, if you look at this red line, it shrinks much faster. Why? Well, obviously because of dark energy term, of course. And I also plot here when omega m0 is 1.1. And this blue solid curve is when omega m0 is exactly 1. And if here is the zoomed view of scale factor as a function of h0 times t minus t0. So in the case of matter plus curvature, the behavior in the beginning was similar, but in this case of matter plus lambda, it's not. They are different from the beginning. Okay. All right. Let's remove right-hand side. Left-hand side. Yeah, left-hand side. Where did I put the? There are too many cases that we discussed today. I'm sure you're confused. What we want to discuss. So let's discuss omega m0 is less than 1. That means omega lambda 0 is greater than 0. So the density contribution between the matter part and the lambda part will in some point equal to each other. So let's call let's rewrite Friedman equation. It's omega m0 over a3 plus 1 minus omega m0. So in some point, the contribution between these two will be equal to each other. So let me read, right? The density contribution becomes equal at equal meaning this size is equal to that size. So that means a m lambda. We call that scale factor to be m lambda. That is equal to this. So let's say 1 minus omega m0 over omega m0 power of 1 over 3. Or this is omega m0 over omega lambda 1 over 3. And in this case, omega lambda 0 is greater than 1, we have another integral to do so. I'll tell you the answer. In this case, let's try to remember all the functions that we saw today. We saw sine, cosine, hyperbolic, cosine, hyperbolic, sine. And just before we saw inverse of sine. What else do we have to see? The answer is the log function. So 2 over 3, 1 over omega n 0, and I have times log a over a max 3 over 2 plus square root 1 plus a over a max out of 3 and closing the log function. It's amazing that there's an analytic solution. There are so many analytic solutions on multi-component universe. But on the other hand, I am showing you only the cases where we have analytic solutions. Now let's discuss this equation a little more. Okay, 3, 5. Let's take a look at this equation at early times and later times. So at early times, A is less than A m lambda. That's what I mean by early times. We have H0T. I'll make a rough approximation. We have this vector 2 over 3 square root 1 minus omega n 0. So this term will be very small because A is smaller than A max. And this term is also very smaller than this term. So I make a binomial expansion. So I'm going to have 1 plus 1/2 of this thing, power of 3. But this a over a max is small number. And this term is power of 3 over 2. This term is power of 3. So this term is much smaller than this term. Am I too fast? Okay. This is log 1 plus a over a max 3 over 2. It's the leading two terms. Where did, okay, all right. And this is log 1 plus something. So log log 1 plus something, when this is very small, it could be log 1 plus epsilon is basically epsilon. So this is approximated as 2 over 3 minus omega m0 a over a max 3 over 2. So now we want to get the expression in terms of scale factor. The scale factor is right here. And we want to get rid of a max. Which we erased already. So we have 3 over, you can confirm this by yourself. Omega m0 h0 t power of 2 over 3. Notice so this is basically a t is t power of 2 over 3, and this is the case when the matter was dominant, when all the universe, which we already discussed. One more thing. I know you're tired. I am also tired. So this was the argument at early times. At later times, dark energy contributes a lot more. Later times, let's go back here. Later times means A is a lot bigger than A max. And if you compare this number and this number, this square root is also a very big number here, but this is very small, so I can neglect this. Then this first term and second term are essentially same value. So because of that, we have H0T is approximately, again, this factor 2/3 square root 1 minus omega m0. Now I have log. I have two of such terms. So A over A max power of 3/2. And then I finally also want to have a dependence. Which color is this? A in this case. A is here, log. So I need an exponential function. So it's roughly AM lambda that we find here. And exponential square root one minus omega m0 h0 t. So it's representing the exponentially expanding universe. So this is just form of exponential some vector times t, and this vector is positive, obviously. So it's expanding universe. And the figure that I just showed you had such a feature at later times. I want to discuss one more thing, but you're tired. I am tired. I'm sorry that today's calculations were a little heavy, but don't be fooled by this heavy calculation. What we are doing is trying to get the expansion history of multi-component universes. And it's okay not to be able to calculate all these mathematical details, but it would be nice if you do it. But what's more important is to be able to get some feeling on several cases that we discussed. Let me stop here today. Any question? Let me stop recording anyway.